Okay, let's quickly summarize what we learned yesterday. We began with reflection of light, and there we have seen that whenever we talk of reflection of light, we should consider three different surfaces. One is a plain and smooth surface like that of a mirror, which we are familiar with, and when light falls, say we consider a parallel beam of light which is shining on this mirror. If this mirror is a smooth reflecting surface, then this is incident ray and this is parallel. So for all these incident ray, there will be a corresponding parallel reflected. And the reflecting surface, we draw a normal. So when the reflection is from such a smooth parallel surface, the angle of incidence is equal to angle of reflection. And such reflections are called specular reflection, where angle of incidence becomes equal to angle of reflection. Then, however, most of the surfaces that we normally encounter, they are rough with lot of irregularity. Maybe such roughness or irregularity cannot be visible in the naked eye. So I showed here microscopic view of such an irregular surface. The surface can be just like this page of the paper where you are probably taking notes of this class. That also would not be a surface like this, it would be irregular surface. So here, if this parallel falls, then you can see clearly that the angle of incidence will be different at different points where this ray of light interacts with this surface. So here, the angle of incidence will be such, but at every point, the reflection will follow the rule of reflection. But if you see overall, they will, because the angle of incidence is different, so the reflected light will travel in different directions. So such reflection is normally termed as diffuse reflection or non-specular reflection. This is specular. There is another surface that we must also consider, that basically is an interface which separates two optically transmitting medium. So one could be air, the other could be water, or it could be air glass. So there, if light falls on this surface, and if we consider the surface to be smooth and wriggle-free, then once again specular law of reflection will follow. However, there is an important point that we must consider is part of the light will be reflected and the other part will travel into the second medium. This air-water reflection from air-water is very common in nature. Let us consider the reflection from such a surface, such an interface. And suppose there is an object, so the image, the formation of the image, the light that shines on the object would be light from this object would shine onto this air water interface in this particular case. So part of the light will be reflected, the remaining part will actually be transmitted to the water. So the image of this would actually be formed here under the water. And if you take all the points of the image, it will be somewhat like this. But the important point that I would like you to note here is that generally the intent, this image would not be as bright as that of the object. Let us consider the case of sunlight. It will be absolutely bright, but this image can be much less brighter because part of the light is only reflected, rest of the light escapes into the water. That is why the image often is not as bright as the object. There is yet another kind of reflection that we talked about, which is called retroreflection. Retroreflection occurs. There are some surfaces on which if light shines, the reflected ray travels exactly in a direction opposite to the, in a retroreflected surface, the light falls and the reflected light travels to incident light. This is reflected light. So the reflected ray travels exactly in a direction opposite to the incident light. An example of such a retroreflector can be thought of two plane mirrors which are inclined to each other at right angle. It would be easy to show here that an incident ray, after reflection, it will be reflected from two reflecting surfaces, will travel, the reflected ray will travel exactly in a direction exactly opposite to the incident ray. So this is called retroreflection. Retroreflection has many uses. Like one use that we will of course study more as we move into this course deeper is this was used to measure the retroreflection property was used to measure the distance from Earth to Moon with an incredible accuracy by making use of a laser. For this, in one of the trips to the moon, when America undertook its lunar mission in early 1970s and late 1960s, then during one of such trip to the moon, an astronaut had placed such a retroreflector on the surface of the moon. This is the moon. I'm giving you a very qualitative picture. Subsequently, a laser beam, highly directional laser beam, was aimed from the ground station to this mirror, which was earlier placed on the moon. So this was a highly directional beam of light, laser beam. Actually, a helium neon laser was used for this experiment. And we would learn more about helium neon laser very soon. So this, after this retroreflection, returned to the right, to the ground. And from the measurement of to-and journey of this beam of light, from Earth to Moon and back to Earth again, the distance from Earth to Moon was estimated to an incredible accuracy, which I think was less than even 1 part in 20 billion. It's such an accuracy. All right. After retroreflection, we studied refraction. In refraction, light travels from one optically transparent medium to a second, which is also optical. Let us assume this interface separates medium 1 and this is medium 2. And light falls from medium 1 on the interface. At this point, we draw the normal on the reflecting surface, the normal, and this is suppose the angle of incidence I. Then light enters the second medium, but it bends while entering, and it can bend both towards the normal as well as away from the normal. Let's just, for timing, let us consider away from the normal. So this is the angle of refraction. And part of the light, of course, returns back to the incident medium, which is, of course, reflection. This is the same that we just studied, reflection on an interface between these two. So now, the amount of bending, see, it has bent now. This amount of bending was first analytically expressed as a function of the refractive index. So this is mu1, this is mu2. Refractive index of the two media by a Dutch physicist, Snell. And the relation between mu1 and mu2 and angle of incidence, I and R, is this mu1 sin R equal to mu2 sin R. This is known as popular as Snell's law of refraction. From here you can clearly see that if the light travels from a rarer medium to a denser medium, that means mu1 is less than mu2. So from this equation, you can clearly see that the product mu1 and sin I should be equal to mu2 into sin I. Now if mu1 is less than mu2, then I sin I must be greater than sin R, or I must be greater than R. So if light travels from rarer to denser medium, then this beam will bend towards the normal. So this will be our R. And if mu1 is greater than mu2, that means light is now traveling from denser to rarer medium. Then, so now mu1 is more than mu2. So now, if mu1 is more than mu2, then sin I should be less than sin R. Hence, I should be less than R. Now, this, from here, we understood that there could be another very interesting kind of reflection, which is known as total internal reflection of total internal reflection of. For this, we will once again begin from the refraction of light, but in this case, light travels from denser to rarer. So, this is denser and this is rare. Light travels from denser to rarer. This is going up. This is the angle of incidence. If light travels from denser to rarer medium, light will have to bend away from the norm. We just saw. It directly follows from Snell's law. mu1 sin I equal to mu2 sin I. mu1 is more than mu2. If mu1 is more than mu2, then I must be greater than R. It's traveling from denser to rarer. So light bends away from phi. So this is what angle. Now let us increase this angle of incidence. So we now increase the angle of incidence. So now what will happen? The angle of refraction will further increase. We increase it even further. And let us assume that in this case, the angle of refraction becomes 90 degrees. That means the refracted ray just grazes over the interface. So for this angle of incidence, the refractive angle has become 90 degrees. This angle of incidence actually is denoted as critical angle of incidence. It is denoted as theta c, critical angle. This critical angle of incidence is that angle of incidence for which the angle of refraction becomes 90 degrees. Or in other words, the refracted ray grazes the interface between these two. So now you see, if you increase the angle of incidence just a little, there is no more scope for light to be refracted, because the angle of refraction has already reached the maximum possible, that is 90 degrees. So then what will happen? The entire light would now reflect. Entire light now would reflect back into the denser medium, because there is no scope for the light to be refracted. This phenomena is called total internal reflection of light. I also told you that this total internal reflection, this property can be exploited to send light through optical fiber without any loss of energy, without any spillage of energy through refraction. So what you basically have to say, optical fiber is a thin glass tube, flexible of course, some kind of glass. You launch your, now this is glass and this is air. Now glass is denser and air is rarer. So in this interface, if light falls, then after refraction, the angle of refraction will become more. So it qualifies this. Total internal reflection can occur on this glass to air interface if light is falling on the interface from glass, from the side of glass. Now you launch your beam, in such a way that this angle of incidence, theta, angle of incidence is I is more than critical angle, which is theta c. So this light will then be totally internally reflected because there cannot be any refraction. Angle of incidence is more than critical angle. So the light now will be reflected and will fall on the other side of that glass and air interface. So here again, the angle of incidence will be the same, which is more than the critical angle. Therefore, here again, it will be reflected. And it will continue to travel through the fiber to such zigzag paths. Every reflection, it will follow, it will be totally internally reflected. Eventually, it will emerge from the other end. Although I have shown here just a small tube, but in reality, it can be very, very long. Even today, we have some optical fiber where you put light at one end, and it can travel almost 500 kilometers, the length of the fiber, without any appreciable loss of energy. Because there is no loss of energy through spillage due to refraction. And also, you choose your wavelength and the glass in such a way that that wavelength doesn't exhibit any loss in the fiber material. So the light can travel very long distance, as I said, 500 kilometers. And you can dump almost seemingly endless amount of information because the frequency of light is much more than microwave or radio wave frequencies. We will come to it later during the course. So you see, you exploit the property of total internal reflection and you use it to today. This optical communication network actually forms the backbone of today's communication network. Most of the data that traverses across the globe makes use of this optical. And perhaps you don't know that today total length of optical fiber that has been laid under the ground, under the sea, under the ocean, total length is, if I remember correctly, it is 450 million kilometers, which is, I think, more than 3 times the distance between Earth and Sun. So you see the power of total internal reflection. Well, after this, we study another interesting, which is called dispersion of light. Dispersion of light was first conceptualized by, perceived by Isaac Newton. He first experimentally established that the light that we get from sun is actually white light. But it comprises of multiple colors like violet, indigo, blue, green, yellow, orange, red. He showed that if this white light shines on something which has a refractive index different from the air. For example, he used a prism, and he showed that when white light shines on one of the surface of the prism, then it would of course be refracted into the prism. This is air, this is glass. So it would be refracted. It would be refracted into the prism, but he found that after refraction, this components, color components actually are being refracted in different angles. For example, the violet color underwent maximum bending, and the red color experienced the least bending. On the second surface, of course, this splitting of these different wavelengths will be even enhanced, will be further enhanced. So this phenomena is called dispersion of light. This prismatic dispersion that Newton perceived some 3 centuries ago, 300 years ago, today is being used for tuning a laser. You have seen in one of the earlier classes that inside the laser cavity, inside the laser cavity, you put a prism, and then of course you have the output mirror here. The prism, if suppose this has multicolor, that means many modes. So this prism will split the modes depending on their color. So different mode will shine on the mirror, different angle. So only one at a time will fall normally. Therefore, this alone will be able to oscillate back and forth inside the cavity and thus less. By tuning either the prism or this mirror, you can choose different modes. So this helps you to get a single mode laser and also allows you to tune the wavelength of the laser by tuning the prism or the prism. All right, I end here, but we soon get into the next topic, which is interference of light.